Homework 17. Copper can be displaced from its oxide by heating with sodium. So we've got copper oxide there, and the purpose of this reaction is to make copper. Okay, copper oxide is sometimes known as copper ore. It's dug out of the ground. That's how we find copper in the environment. To make it useful for wiring and electronics, we need to remove the oxygen, chemically remove the oxygen. One way of doing that is displacement, where we react the ore with a more reactive substance. And that displaces the copper. So in other words, the copper loses the oxygen to the more reactive substance. Sodium is more reactive. So sodium oxide is produced because sodium takes the oxygen, leaving copper on its own. Okay, in this reaction, something is oxidized. Oxidized is taking the oxygen, so you need to decide what's taking the oxygen, and something is reduced. Reduced is losing the oxygen, so something is losing the oxygen on the left here. Okay, so oxidized is one of these, and reduction is one of these. Okay, oxidation is gaining oxygen, reduction is losing oxygen. What mass of sodium is needed to produce 124 grams of sodium oxide? So this is calculating quantities, and the first thing we need to do is put this information on the equation. So what mass of sodium? The Na there is the sodium, so that is the question mark. Okay, is needed to produce 124 grams of sodium oxide. Well, that's a sodium oxide, 124 grams. Okay, so with all these calculating quantities, these moles calculations, it goes moles, stoichiometry, and moles. So first is moles, second is stoichiometry, third is moles. Now moles equals mass over atomic mass. Now in stage one, we always do the moles of whatever we wrote the mass on top of in the equation. Now this time we wrote the mass on top of the sodium oxide, so we need to start with sodium oxide. So instead of saying atomic mass there, I probably should say formula mass, because that's a compound MR. Notice it was mass divided by formula mass. We're going to do it for that one to start with. So what you need to do to start with here is calculate the formula mass of sodium oxide, and sodium oxide is Na2O, so Na plus O, and the mass is going to be that 124. That will tell you the number of moles. Your atomic mass is there. Once you've got the number of moles of sodium oxide, we need to go to stoichiometry. Now, this will confuse some of you because we seem to be going backwards, but that's absolutely fine. It doesn't matter how you write it. You could write it like this, which is exactly how the equation is written out. Okay, makes 1 Na2O. There's no number before the Na2O, so there's a 1. And to get from there to there, okay, we're just going backwards. That's absolutely fine. To get from 1 to 2, well, 2 is bigger than 1, we had to multiply by 2. This is a doubling relationship going that way. So whatever number of moles you work out here, you're going to write there, and then you're going to do exactly the same, multiply by 2 to get the number of moles of sodium. Okay, so whatever that number is there is going to come up here now, because we're going to rearrange this moles equation into stage 3 to make mass the subject. Mass equals moles times, and we will use AR this time, atomic mass, because this is sodium. Now remember that big 2, that's a stoichiometry number. We use it here. Okay, so it's just the atomic mass of sodium. So it's just going to be 23 that goes in there, not 46. And that moles number we calculated in stage 2, that's going to come up and go just there. So let's move that over, just there. And whatever that times 23 equals, that is going to be your answer in grams. What's reduction? Well, we stated that a moment ago up here. There's two definitions for reduction. It's the gaining oxygen, losing oxygen definition we had up here for oxidation and reduction, and there's also oil rig. Okay, I don't mind which one you write down in this homework, oil rig. So, and that's to do with electrons. I'm just going to leave that there, and you can go back and look it up in your book if you're not quite sure what I'm talking about. So, iron is extracted from its ore by heating with carbon, whereas aluminium is extracted from its ore with electrolysis. So let's just be clear about this. Iron is found in the ground as iron oxide. Aluminium is found in the ground as aluminium oxide. In other words, iron ore or aluminium ore. Now, there's two methods of extraction. You can extract by heating with carbon. Okay, extract by heating with carbon, and that works because carbon is more reactive than the iron. So it takes the oxygen away, making carbon dioxide and leaving the iron ore on its own. Okay, so the carbon is more reactive, it takes the oxygen, therefore makes carbon dioxide and then leaving the iron on its own, which we can then turn into cars and bridges and girders and things like that. Aluminium oxide is extracted using electrolysis. Electrolysis is where we have, this is an ionic substance, so this has to be a liquid or dissolved, and they dissolve it in cryolite, but you don't need to know that. And we use DC electricity, direct current electricity, and the electrolysis decomposes this compound into aluminium and oxygen. Okay, neither of those equations are balanced. So electrolysis, you may say, well, why don't we use electrolysis for iron oxide as well? And that's what this question is about, really. Why do we use electrolysis here, but yet displacement here? Well, aluminium is very reactive. Aluminium is very reactive, so aluminium is more reactive than carbon. So there's no way displacement will work. So simply displacement will not work for this. That's why electrolysis is used. So you then say, well, why don't we use electrolysis for iron oxide as well? If it works for aluminium, will it work for iron? And the answer is yes, it will. It would work extremely well indeed. So why don't we use it? Well, electricity and generation of electricity is expensive. Okay, displacement of carbon is just a much cheaper process, and that keeps the price of cars down and things like that. So you need to write that answer into there in your own words. Next question. When iron is extracted from iron oxide, Fe2O3, it's heated with carbon to form carbon dioxide as well as iron. Write a balanced symbol equation for this reaction. Well, there was a little bit of help I just gave you in the previous question there. You can go back and have a look at that. You will notice, however, you still need to balance. What mass of iron is produced from 20 tonnes of iron oxide? Well, we were told a moment ago, Fe2O3 made iron once it was displaced. Okay, so that's a fairly easy equation to balance. So let's just work with that, because we can establish that from this question here, because we're told it's Fe2O3 and we're told it makes iron. So we don't actually need to worry too much about the rest of the equation, because we cross those bits out anyway. We can just work with this one. So what mass of iron, that's the question mark, is produced from 20 tonnes of iron oxide? Again, calculating quantities. So step one, moles equals mass over mR. 2, stoichiometry. And 3, moles, where you're going to rearrange that equation to make mass the subject. Mass equals moles times, that'll be atomic mass there. Okay, so in stage one, you calculate the number of moles of whatever we've written the mass over. So you need to calculate the formula mass of that. There are the atomic masses, that will be mR. Mass will be 20 tonnes. Stoichiometry, no number before the 1 here, so let's just write this out again. Fe2O3 makes 2Fe. There's no number before the Fe2O3, so there's a 1 there. So how do we get from 1 to 2? What do we have to do to 1 to make it into 2? Whatever you do to that, you're going to then write the number of moles you calculated in stage 1 here, and whatever you did to 1 to turn it into a 2 mathematically, you're going to do the same here, and that will be the number of moles of Fe. That number there is then going to go up there into moles times the atomic mass of iron, which you've got, so you can write the atomic mass of iron there. And once you've done that, you've got your answer. Now the answer is going to be in tonnes, because we started in tonnes. The final question. 11 grams of another oxide of iron. Well, let's be careful here. Okay, I'll come back to that in a moment. Contains 7 grams of iron. Calculate the empirical formula. Right, so empirical formula, divide the bit of paper in half, just down to about 3/4 or 2/3 of the way. On one side, you're going to write iron, okay, Fe. I'll just put a symbol. On the other side, you're going to write oxygen. Okay, and then you're going to write moles equals mass over atomic mass here, and moles equals mass over atomic mass here. and you're going to write the mass down. Now, iron, 7 grams of iron. So that's 7 grams there, divided by the atomic mass 56. So you're going to do that, and then that's going to be Fe, whatever that answer is, that's going to be that part of the formula. Okay, now this is where we need to be careful. 11 grams of another oxide. Where every student goes wrong is they write 11 there for mass, but they haven't read it carefully. 11 grams of another oxide of iron. So that's 11 grams of the compound. So we've got 11 grams of this compound, FeX. OY, I'm going to call it. So there's 11 grams of that. We're told it contains 7 grams of iron. If it contains 7 grams of iron, okay, what's the mass of oxygen in there? Well, it's 11 in total. 7 of it is iron, so we need to take the 7 from the 11. So that's going to be 4 grams. That's why we need to be careful. So the mass here is going to be 4, because we're going to do 11 minus 7 equals 4. Okay, let's just go through it again. Let's think about it for a second. If my and my wife's combined weight is, I don't know, 30 stone. Okay, it's not. My wife's combined weight, so we're both standing together on a scales, and the scales reads 30 stone. I get off and my wife is 10 stone. How much do I weigh? That's what we're doing there. And you can all shout 20 stone. No, I'm not 20 stone, but you get the idea. Okay, and that's what we're doing here. The whole mass of the compound, this other oxide of iron, okay, is 11 grams. 7 grams of it is iron, so we need to subtract these two to get the 4 grams of oxygen. That's why that's a more difficult empirical formula question. Okay, so the mass is going to be 4 divided by the atomic mass. You can write that in, and whatever number we come up with there, that's going to be the empirical formula. Almost, because we then have to report that to the smallest possible whole number. So when you've got these numbers here, ask yourself a couple of questions for me. First question, can you ask yourself, are these numbers the same? If the numbers are the same, then it's a 1-to-1 ratio. You can just write FeO. Okay. If they're not the same, ask yourself a question, which number is bigger? If the O is bigger in the final formula, which you're going to write down here, if the O is bigger, then it has to be bigger down here. If the Fe is bigger, it has to be bigger down here. Okay? So, which number is bigger? Because that's got to be bigger at the end. And the final question, how much bigger is it? Now, let's just say, for the sake of argument, this is Fe, I don't know, 0.1. Okay, and that's O, 0.6. It won't be. Okay, obviously, this O is bigger. Okay, that's bigger, so the final number has to be bigger. And we're looking at the relationship now, how much bigger? Well, hopefully you can just see that 6 times bigger, can't you? So the answer will be FeO6, all right, because that is bigger and it's 6 times bigger. Now, if you can't see how much bigger it is, take the big number and divide it by the little number, and it will tell you exactly how much bigger it is.